Hello student, hope you all are in good health and at home. So let us start with electronics paper 1, applied electronics. Student, we already started with chapter number 4, operational amplifier. So this is the third lecture. So let us see what we are seeing in the first two lecture. Very fast revise that. So we are seeing what is an amplifier, then what do you mean by operational amplifier, then we are seeing schematic symbol of an amplifier, operational amplifier or op-amp. Then we are seeing the pin diagram of op-amp, that is IC741. Then we are seeing internal block diagram of operational amplifier. In the second lecture, we have seen the characteristics of an ideal op-amp. Then we have seen the specification of IC741. Then we have seen the parameters of op-amp. So, parameters of an op-amp, we have seen the first parameter, that is input bias current. The second parameter, input offset current. So in last lecture we have completed till that we have completed two parameters. Today we will see the remaining parameters. Input offset voltage VIO. So let us understand the next parameter, that is input offset voltage VIO. Now to understand this input offset voltage, let us assume that both the input terminals of this op-amp are grounded to zero potential. So both inverting and non-inverting terminal are grounded to zero. And if the op-amp is ideal and we consider this op-amp to be a ideal, in that case the output of the op-amp should be equal to 0 volt. But actually if you see, you will find some finite voltage at the output terminals of the op-amp. So let us understand why this finite voltage appears at the output terminal even though the input terminals are grounded or input terminals are 0. So this is due to the slight mismatch between the two transistors of the differential amplifier. We have seen the internal block diagram of the op-amp. The first stage is differential amplifier, where we make use of a two transistor. So there is a slight mismatch between the two transistors of the differential amplifier, and because of that both the transistors have different biasing voltages. Let VB1 be the biasing voltage of the non-inverting terminal and VB2 be the voltage biasing at inverting terminal. So the slightly mismatch between the biasing voltage, there is a potential difference between the two terminals, and this potential difference, so here the voltage biasing voltage is VB1 and here the biasing voltage is VB2. Because of the slight difference we get the biasing voltage, and this biasing difference between the biasing voltage, that is VB1 minus VB2, the potential between these two is used to get amplified at the outer stage, and because of that we get the offset voltage at the output, and because of this biasing voltage we get the voltage at the output instead of getting 0 volt, right? So suppose if we apply a differential voltage, a differential voltage at the of opposite polarity at one of the input terminals, we can ensure that the output of the op-amp, that is 0 volt. So the error voltage that is appearing at the output, even though the inputs are grounded, this error voltage, to nullify this error voltage, we connect a potential difference of opposite sign. See, if you are getting a positive error, we apply a negative voltage at the input terminals, either to the inverting or to the non-inverter. If we get negative error, we add the positive, so that the input voltages will nullify and output we will get at 0 output. right? So the definition of the input offset voltage is the amount of differential voltage which is required to be applied between the two terminals such that the output of the op amp becomes zero. So this is nothing but input offset voltage, okay, that is to be needed to be connected between the input of the op amp so that the output of the op amp will be zero. The op amp will become zero, right? So the input offset can be of few millivolts for the general purpose op amp, and it can also be as low as 1 microvolt. This is in millivolt or in microvolt. That is nothing but input offset voltage. Okay. So when the input voltage to the op amp are 0, the output must be 0. To force this error in the output voltage back to zero, some input is applied at the input terminals. This applied input voltage is called as offset input offset voltage, VIO. Clear? Next parameter, output offset voltage, VOO. When the input voltages to an op amp are 0, then the output must be 0. So we have seen in the previous parameter when we did input offset voltage. Even though the inputs are at 0 potential, we get some output. Okay, due to the some error, the output voltage is other than 0. This error voltage in the output we call as output offset voltage, right? So even though the input terminals are grounded, we get the output voltage. Actually, the output voltage should be equals to 0. So this is the error voltage, and this error voltage is called as the output offset voltage. So the next parameter is slew rate. So the slew rate of an op amp can be defined as the maximum rate of change of the output voltage per unit time, right? Or in other words, we can say that how fast the op amp is able to respond. We have seen when we have seen the characteristics of the op amp, the slew rate should be infinite. When the slew rate of the op amp is low, it produces distortion at higher frequency. It is produced, why it is produced? It is mainly produced due to the internal capacitance and unwanted feedback in the op amp. The slew rate is low due to the internal capacitance and unwanted feedback in operational amplifier. Let us assume that the input side we have applied the square wave. So this square wave is varying from 0 to 5 volt. So at the output side also we should get a square wave. This is our output waveform. Square wave which is varying from 0 to 5 volt. Now here ideally the out should go from 0 to 5 volt in no time. But actually if you see the output will take some time to reach from 0 to 5 volt. There is a delay. See, delay of delta t to reach from 0 to 5 volt. And if you see the waveform, then the actual waveform will look like this. This is the output amplified waveform, right? The time which is been taken by the op amp to reach this 5 volt depends upon the slew rate of the op amp. So the unit of the slew rate is volts per microsecond. So let us say that for a particular op amp, if the slew rate is 1 volt per microsecond, it means that the output will change by 1 volt in 1 microsecond. And for that the op amp to reach from 0 to 5 volt, it will take the time around 5 microseconds. So delta t equal to be 5 microseconds. Okay, different op amp have different slew rate, and the value of the slew rate varies from 0.1 volt per microsecond to 1000 volt per microsecond. For the general purpose IC, that is 741 IC, the value of slew rate is 0.5 volts per microsecond. So in practical we are using 74 IC. For that IC the slew rate is 0.5 volt per microsecond. So slew rate is nothing but the maximum rate at which the output of the op-amp changes. So dV by dt, that is nothing but slew rate. Next very important parameter, that is common mode rejection ratio, that is CMRR. If the two inputs of the op-amp are tied together to the common input voltage, in that case the output of the op-amp should be equals to 0. So we have seen that, right? So this configuration where the two input voltage are equal or two inputs voltage are tied together to the common input voltage, that configuration is called as common mode configuration, right? And the input voltage which is applied to the both input terminal is known as common mode voltage. So in the ideal condition, in this configuration the output of the amplifier should be 0, but actually if you see, some voltage is available at and this output voltage is known as the common mode output voltage. Common mode output voltage, because we are tied together and there is a common voltage at the input, we get this common voltage at the input is nothing but that is a noise, and that produces a common voltage at the output. Clear? So we say that, so what is CMRR? So we can say that the ratio of the output voltage divided by the input is always less than 1. So this ratio or the gain is commonly known as common mode gain of the op-amp. Okay. So common, let us define what is CMRR. CMRR is a ratio of differential voltage gain to the common voltage gain of the operational amplifier. What is this common gain? Common mode gain is nothing but voltage at our common mode voltage at the output upon the common mode voltage at the input. It is a ratio of common mode voltage at the output to the common mode voltage at the input, that is ACM, and ADM is a differential voltage gain. So CMRR, we have seen the characteristics of the CMRR, that CMRR should be infinite. It is a common signal applied to both the input of the op-amp to give the output 0, right? So this is nothing but the, the source which acts as a common mode input signal is noise signal or the electromagnetic for any op-amp. This term should be minimum as possible, as the op-amp should be able to suppress this common mode input signal which is present in both the inputs. And how will it be able to suppress this common mode signal is defined by the parameter which is known as common mode rejection ratio, and it is a ratio of this differential gain divided by the common mode gain. In decibel it can be expressed as 20 log ADM upon ACM. Now usually this parameter is defined for the open loop configuration. But in practical cases, this op-amp is used as a differential amplifier in a closed loop configuration. The value given in the data sheet is for the open loop configuration but can be used for closed loop configuration also. Clear? So CMRR is expressed in decibel, that is dB, and C common mode gain is very small and the differential gain is very large. Clear? That is nothing but common mode rejection ratio. Open loop gain, AOL. It is defined as the gain of operational amplifier without feedback. It is the ratio of output voltage to the differential input voltage. So AOL, that is open loop gain, is given by output voltage to the differential input voltage VO upon VD, where VD is differential voltage across inverting and non-inverting terminals. So here between non-inverting and inverting terminal, this voltage is nothing but VD, right? For ideal op-amp, the open loop gain is infinite. For IC 741, the mid-band frequency, in mid-band, this gain is about 10 raised to 5. But this gain is unstable and is affected by change in the supply voltage, temperature and aging of the active devices. The open loop gain decreases due to the compensating capacitor as the frequency increases. Okay, so this is nothing but open loop gain parameter. Now student, let us see the next parameter, that is closed loop gain ACL. When the feedback network is connected between the output terminal and inverting terminal, some output voltage is fed back to the input terminal, right? That is a closed loop. Okay. So gain of the op-amp with feedback is called as the closed loop gain, and it is given by ACL is equals to open loop gain 1 upon 1 plus open loop gain, and the factor beta is a feedback factor, right? So beta feedback factor. So closed loop gain is given by open loop gain plus 1 plus open loop gain into the feedback factor. This is nothing but closed loop gain. So let us see the frequency response of the op-amp. So here the graph is shown. The frequency response graph of the op-amp shown. See here graph is shown. X-axis we have taken frequency in hertz, and y-axis we have taken voltage gain in decibel. So 20, 40, 60, 80 and 100 decibel, that is voltage gain, and x-axis we have taken frequency. So now so far we have assumed that the gain of the op-amp is very high and it is having a very high bandwidth. Bandwidth is nothing but a range of frequency, and we have assumed that the gain of the op-amp is constant up to certain band of frequency. But if you see the actual response of the op-amp will look like this. That means that the gain of the op-amp will be constant up to certain frequency. It is constant up to certain frequency, and if we go beyond this frequency, then the gain of the op-amp will reduce at the constant rate of minus 20 dB. See 20 dB, there is a fall of frequency, and this frequency is known as cutoff frequency of op-amp. So the cutoff frequency is the frequency where the gain of the op-amp will be reduced by 3 dB. Okay, so it will decrease by, that is nothing but cutoff rate. At any point on the graph, the product of the gain and frequency remains constant. So if we take the gain and frequency constant, it will remain this gain and gain bandwidth product. This is known as gain bandwidth product. Unity gain bandwidth of the op-amp is 1 megahertz, because at this frequency the gain of the amplifier is 1. This frequency is known as unity gain frequency. For high frequency, the gain of the op-amp is low. We have seen because of the capacitor. The bandwidth is nothing but higher frequency minus the lower frequency, but the lower frequency is 0, so bandwidth is equals to higher frequency. This is known as the cutoff frequency at which the gain of the op-amp is 0.708 times that of its maximum gain. That is nothing but, and the gain bandwidth product is the product of gain and the cutoff frequency. Clear? Student, in today's lecture we have seen the parameters of operational amplifier. So we have seen very important parameters like input offset voltage, output offset voltage, slew rate, very important, then CMRR, that is common mode rejection ratio, open loop gain, closed loop gain, and we have seen the frequency response of the op-amp. So here we have seen all the parameters of op-amp. So we came to the end of operational amplifier session 3.